Okay, let's dive into this explainer. Today, we're exploring a truly groundbreaking framework for modern computing. I mean, have you ever stopped to wonder how massive tech companies keep their giant, incredibly power-hungry AI computers from just melting down? Well, it turns out the way we've been measuring safety and efficiency in these huge data centers, it's fundamentally flawed. So we're going to unpack some absolutely fascinating new research by Kevin L. Brown, a researcher, inventor, and author who's figured out exactly how we can safely push the limits of our digital world. Here's our roadmap for today. We're going to cover 1. The hidden data center problem, 2. A 5-dimensional hypothesis, 3. The 5 measurement dimensions, 4. Validating the new model, 5. Falsification, basically how to prove it wrong, and finally, 6. The real-world impact on AI infrastructure. All right, Section 1, the hidden data center problem. We always kind of think that making a system more efficient just solves our problems, right? But in a massive connected physical system, it's rarely that simple. So why do major upgrades in data center cooling or power so often trigger a critical bottleneck somewhere completely different? It's almost like a Trojan horse. Think of it like widening a really busy highway. You spend millions adding an extra lane to fix a traffic jam. But what actually happens? The cars just move faster until they all try to get off at the exact same exit, and bam, now you've got a massive pileup on a local street. You didn't actually eliminate the traffic jam, you just moved it. And in data centers, this is exactly what happens. Upgrading a cooling system might just push all that physical stress straight over to an electrical transformer. For years, the industry has relied on this old way of measuring success, using just a single metric. A single number, like power usage effectiveness, or PUE. If that one number goes down, everybody cheers. But here's the catch. A single number simply can't tell you where the stress just moved. It completely misses those hidden breaking points. A small energy transfer might look totally fine on a single metric, but if it pushes an already stressed component past its absolute limit, the whole system can fail. The new way demands we track a multi-axis physical state, which actually gives us the full picture. Moving on to Section 2, a 5-dimensional hypothesis. This brings us to a concept called constraint transfer. This was proposed by researcher, inventor, and author Kevin L. Brown. Basically, it's the measurable way physical limits and operational stress shift across a connected system. His hypothesis argues that tracking this stress requires a 5-dimensional state, not just a simple single-number ratio. You literally need a multi-part tool to capture the full reality of where the pressure's actually going. In his research, Brown explicitly states, quote, "Constraint transfer in data centers is not a single efficiency scalar. It is a multi-axis physical state." Now, what's really interesting about this is that standard, simple metrics actually misclassify dangerous, physical meltdowns as totally harmless load shifts. Think about it. If you only look at the overall average, a massive power spike that melts a wire looks exactly the same as a totally safe, even spread of power. We absolutely have to look at the different axes, the different dimensions, to know if we're actually safe. Section 3, the 5 measurement dimensions. So what exactly are these dimensions? Instead of one number, the state is made up of these 5 specific steps. First, we've got aggregate transfer, which looks at the overall movement of the load. Second is peak strain, watching out for those instant, dangerous overloads. Third is exceedance exposure. This tracks how long and how bad an overheating event actually is. Fourth is the relief mechanism, basically asking, how did we cool things down? And fifth is the induction mechanism, tracking where the new stress popped up. It might sound a little technical, I know, but together, these track everything from a harmless moving load to a literal physical safety trip. Let's see how this builds. When you put these pieces together, it becomes an incredibly powerful tool. By looking at aggregate transfer right alongside peak strain, this method completely separates harmless load shifts from the really dangerous, near-limit overloads. It also asks the important why and how questions. For example, the relief mechanism tells us if a cooling fix worked because we actually lowered the heat being generated or if we just turned on more air conditioners. It's literally the difference between treating the symptom and treating the disease. Section 4, validating the new model. Now, obviously, a great idea is only as good as its proof. To validate this hypothesis, the framework is tested against hidden data, information the model hasn't even seen yet. And the results are fantastic. It predicts facility faults way better than the older models. One of the smartest features here is how it uses duration rules. Have you ever had a smoke detector go off for 1 second just because of a tiny speck of dust? That's sensor noise. Well, this model is smart enough to filter out those random 1-second sensor spikes, so it only raises the alarm for real dangerous thermal violations. It can actually forecast a bottleneck moving before an expensive upgrade is even built. How cool is that? And this brilliantly illustrates the point. When it comes to predicting when a data center system will actually fail, older single-metric and multi-objective models, they fall drastically short. But this new 5D constraint state heavily outperforms them, giving engineers a seriously accurate map of where a failure is going to happen next. Part of why it works so flawlessly is a unique mathematical tool called zero-safe Shapley attribution. Older models would literally break and throw error codes if the system demand dropped all the way to zero, kind of like trying to divide by zero on a calculator, right? But this math rule totally solves that. It perfectly tracks whether a fix came from lowering the heat or adding chillers, and it works without a hitch even when parts of the system temporarily shut down.
Section 5. Falsification. Proving it wrong.
Any real science has to state exactly how it could be proven wrong. So Kevin L. Brown included a super strict pre-registered protocol laying out exactly what would cause this framework to fail. For instance, if independent scientists can't perfectly reproduce the math, or if just drawing a different boundary on the map changes all the results, the model fails. Also, if its time filtering rules accidentally ignore a real physical violation, like a genuine fire risk, the hypothesis is totally rejected. This level of strict scientific rigor gives us incredible confidence in the model. It's not hiding behind vague claims. It's putting all its rules right on the table for everyone to see. Section 6. Real-world AI infrastructure. So what happens when we take this out of the lab? Well, it all comes down to the number 5. So the crucial point is, tracking these 5 dimensions is the ultimate key to safely scaling massive computing power. As we build bigger, more powerful AI systems, we're pushing the physical limits of electricity and cooling, and we simply cannot manage that kind of scale with just a single average number. We need all 5 dimensions. The real-world implications of this are absolutely massive. By adopting this framework, tech companies can safely deploy incredibly power-hungry AI cloud systems without triggering any hidden meltdowns. It allows engineers to forecast exactly where the next bottleneck is going to be before they spend millions of dollars retrofitting a building. It catches those hidden thermal spikes that older systems would completely ignore, ultimately guaranteeing the physical safety of the facility. It literally keeps the cloud from catching on fire. Which leaves us with this final thought. As AI computing demands continue to push our physical infrastructure to its absolute breaking points, can we really afford to keep measuring our success and our safety with just a single number? Understanding the 5-dimensional physical constraints of the cloud is no longer just some theory. It's an absolute necessity for the technology we rely on every single day. Thanks for joining me on this explainer, and I really hope this sparks your curiosity to look a little deeper into the physical world powering our digital lives.